I've started the recording now. Just to let you know, we've got on the call today, we've got Mathilde Riepart, who is the PhD student who has done most of the development of this algorithm. So just to start with a really big thank you to Mathilde for all her hard work putting this together. And also Dr. Hannah Spitzer, who's not on the call today, but who has also done a huge amount of the development. I'm Dr. Sophie Adler. I co-lead the project with Dr. Conrad Wagstill. And just a big welcome to everyone. So we've covered today, so before we start, if you go back to Mentimeter and just let us know, the next question is, have you...
So this is a really nice overview of where everyone's joined, and we're just going to move to the next question now, which is...
Have you used a MELD classifier before? Have you downloaded and installed? So we just wanted an idea of who's on the call and whether people have or haven't tried using any of our code before.
Give a couple of minutes just to get used to the get some answers.
I mean, I have given it a fair trial.
Yes, I think we have the next question that might be more direct for that then. Okay, I can see we've got 50 on the call and we've got about 30 responses. So for those who haven't been able to respond, we encourage you to go to menti.com and use the code 88010577 at the top, and that will show you these questions that you can then answer, and we can just input.
So we've got a mix on the call today. Some people who have used our code, some people who haven't, and I think we know of a few who've tried and haven't managed to. So we'll be targeting this for everyone. So we'll be starting kind of from the beginning, as if you don't know anything about our code or our algorithms. And so the next question, which is our newest algorithm, the MELD Graph classifier, is: have you installed it? Have you tried, or have you got stuck? And it looks like we've got a mixture.
We're at about 35 responses, which is, I think, half of everyone's got on to Menti, which is great. And we've got a nice range.
So we've got a few people who've managed to install the classifier. We've got quite a number who haven't tried yet. And then we've got some who've got stuck. So do a bit later on when we get to installation, or you could start posting in the, but later we'll try and hopefully help with that.
Okay, and then I think the next one. Oh.
And lastly, in terms of what you're hoping to get out of today's workshop, would you like to just learn about the MELD classifier? Would you like to, by the end of this, really be able to try running it? And would you like to learn more about how to actually look at the outputs and interpret what they have?
Okay, great. I think a few more people have managed to get onto menti.com. We've got...
Okay, so we've got basically a lot of people wanting to learn about the classifier, a lot of people who are wanting to try the classifier, and a lot who are also wanting to learn about interpreting the reports. And hopefully we'll be able to cover all of that today.
Okay. So, presentation.
So the plan for today is firstly just to give you an overview of the MELD Graph algorithm, and then to run an interactive notebook, which kind of goes under the hood, looks at how the classifier works, what the features look like, and what goes into the algorithm, and then the outputs. And then finally to look at the MELD Graph outputs and how you can interpret them and how you can quality check them. We'll then try and have like a short break. And then afterwards will be the much more, this is what you type into your terminal window. This is how you prepare your data, how you compute your harmonization parameters, and how you run the prediction pipeline. So We started trying to develop these algorithms based on children like this 8-year-old girl who was referred to Great Ormond Street Hospital with drug-resistant focal epilepsy. She'd had an MRI scan under the epilepsy protocol, and it had been reported as looking normal. And this is what we call our, MRI negative patients, the ones where we suspect there might be a structural lesion causing their epilepsy, but we can't see it on the MRI. And we know that 30% of patients with epilepsy are drug resistant, and surgery can be a safe and effective treatment if a lesion can be found. So we started the multi-center epilepsy lesion detection project to try and bring imaging and AI together to better understand, diagnose, and target treatment in patients with drug-resistant focal epilepsy. And when we talk about MRI negative epilepsy, in 2 cohorts, both in adults and in children, where they had MRI negative epilepsy but had been operated, they looked at what the underlying histopathology was, and around half of these cases are focal cortical dysplasias. So focal cortical dysplasia is the most common MRI negative pathology, and it's where we wanted to start in terms of developing an automated method to find MRI negative epilepsies. So focal cortical dysplasias are malformations of cortical development, and they can have subtle imaging features. So on the right-hand side, you can see a coronal MRI scan of a patient. Ooh. Here you should be able to see an MRI scan of a patient with a focal cortical dysplasia. I've taken you to the right coronal slice, and if you go to menti.com and use code 88010577, if you could let us know, where do you think the focal cortical dysplasia is? There's boxes on the right-hand side, A, B, C, D, E, F, G. Okay, and so in terms of the features that you're looking for an area of abnormal cortical thickness. You're looking for blurring of the gray-white matter boundary. You're looking for, on the flare, any flare hypo or hyperintensities, and you might see a transmantle sign, which is a hyperintensity extending from the gray matter to the white matter, to the ventricles. You might see some hemispheric asymmetries, or you might see you might see some hemispheric asymmetries or just some folding changes. So we have a spread of where people think this lesion is. In fact, we have quite an expert audience, and 13 have got it right. The focal cortical dysplasia in this case is B, and you can see that it does have a nice transmantle sign going from the grey matter down to the ventricle. But the aim of this workshop is to hopefully, you can see that lots of people don't know where this lesion is, and the idea would be that you would be able to have an automated way to find these subtle focal cortical dysplasias. And if we just go back, now that you know where it is, what features do you think, characterize this focal cortical dysplasia? Transmantle, do you think it has any of the other features on the MRI that I just described? See if anyone else wants to put anything in. It is a focal cortical dysplasia type 2B. It does have a transmantle sign. I think it also, yes, somebody's put blurring. I agree. I think that you can see on the T1 blurring at the gray-white matter boundary. You can see hyperintensity. Yes, blurring of the gray-white matter junction. Brilliant. Okay, so we'll go back to the slides now. So to create an AI algorithm, we needed a large data set. And so we worked with 22 epilepsy surgery centers worldwide. And I know a lot of people who contributed data and collaborate with us are on this phone or on this workshop. So a big thank you to all of them. This was a cohort of pediatric and adult patients, either scanned on a 1.5T or a 3T MRI scanner. And we had over 1,000 participants, 618 with FCD, and around 400 controls. And what each center did was they created these surface-based features that I just described, like cortical thickness, and that Conrad will go into more detail of in a minute. But they also had radiologists or experts at their center manually mask on the MRI scan where the focal cortical dysplasia was, so that we could train our AI algorithms to find these lesions. So this is supervised learning, where the algorithm is trained knowing where the abnormality is on the training data set. And so the first thing that we could do is, with this cohort of over 600 patients, is look at where in the cortex do these focal cortical dysplasias occur. And what you can see here is blue is lower numbers of lesions and red is higher numbers of lesions in that location. And so you can see that anywhere in the cerebral cortex, you can get a focal cortical dysplasia, but that there are certain hotspots where we see more of them. And those include the frontal pole, the temporal pole, the superior temporal gyrus, and the superior frontal sulcus.
Okay, so thank you, Sophie. I'm going to take a little bit through the pipeline of how we both extract those features and train our algorithms to find the lesions. So Sophie talked about the abnormal features that you see in an FCD. That would be cortical thickness. And so we can measure the thickness of the cortex using our free surface reconstruction. So we reconstruct the inner and outer surfaces of the cortex, inner and outer surfaces of the gray matter, and then we can extract these features. Thickness is one. We can quantify the contrast by sampling the T1 intensity inside the cortex and in the white matter just underneath the cortex, and that ratio becomes the contrast. We can look at the intensities of the flare or T2 weighted MRI by sampling both in the cortex and then underneath the cortex if we want to capture some of the transmantle sign. We can have a look at abnormalities in the folding pattern by measuring the curvature, the sulcal depth, and intrinsic curvature, which is a metric that we helped to develop to kind of really highlight where these folding abnormalities are. And then we can also look at left minus right, which is that feature that we will do when we look at the scans, but we can do this quantitatively, subtracting the left from the right and the right from the left to look at the asymmetry of all of these features. We then do a number of harmonization and normalization steps to help really highlight what's abnormal. So harmonization helps to deal with the fact that at different scanners, the way they measure these features might be a bit different. So the numbers that they use for T1 intensity might be a little bit different. You need to adjust for that. Or a scanner might measure cortical thickness as being thicker or thinner on average than for a new site. We also do a number of normalization steps. So intrasubject normalization helps to deal with changes, for instance, to do with age. You get thinning over age or between male and female. We also do, as I said, left minus right, so that's asymmetry. And we do normalization by controls, and this is to deal with the fact that different parts of the brain have different structure. So the frontal cortex might be thicker than the occipital cortex, and to know what's abnormal, you need to know what's typical for that brain area as well. Once we've done that pre-processing, we can have a look within the manual lesion masks at whether we are capturing features that are abnormal. And so this is a UMAP plot where we've averaged the features inside each patient's lesion mask, and that's a point. And then points are much closer together if they have similar features. And then we can color the points by what those features are to see what patterns we see in our data set. So in the top left, we have intrinsic curvature, this folding score, and it's pretty abnormal in most of the patients. The red is high and abnormal. Cortical thickness tends to be increased, but there are some in whom it's decreased. The gray-white matter contrast is almost uniformly decreased, so you get blurring in almost all patients. Sulcal depth is not a particularly sensitive or specific measure, but you do see a group that might be considered this bottom of sulcus group here at the top. We have the flare intensities, which tend to be lower inside the cortex, so hypo-intensity on the flare gray matter and hyper-intensity on the flare white matter. And this group up here, when we looked at the histologies, tended to be the FCD2Bs. So this is probably the transmantle sign that we're picking up here, this hyper-intensity in the white matter. So I think 2 points to take away from this is that these features are abnormal in the lesion, and that's a useful thing to know. And also that the lesions are quite heterogeneous. So a simple machine learning algorithm might not be able to identify all the different types of lesions. And this is why we started to move towards deep learning to solve this problem, to recognize all these different types of lesions. And so we ended up with a pipeline, and I'm just quickly going to introduce the pipeline from 2022, which is per vertex. We also called it the multi-layer perceptron, MLP. It has this feature extraction, harmonization, which I've discussed, which adjusts for site differences, normalization steps that I've just gone through, the intrasubject, the asymmetry, the normalization by controls. And then we train with a train cohort and test on a withheld test cohort. And in this first classifier, we were looking at points on the surface in isolation. So at every point of the surface, we said, well, does this set of features look like a lesion or healthy cortex? And in that paper, it performed pretty well. But the feedback we started to receive is that it was producing quite a lot of false positives. So you get clusters in different parts of the brain that were for other reasons that weren't FCDs. And we thought this was because it was looking in isolation, doesn't know about what's going on. This AI only knows about what's happening at that point on the brain and doesn't have this context to be able to rule out other false positives. And so MELD Graph is really designed to address that issue. It's trying to reduce the number of clusters predicted. And the way we've done this is exactly the same data goes in, the same patients, the same training set, and so on. But instead of looking at each point on the surface, we now know we have this kind of, it's called a convolution. We know where the vertex is, but we also know its neighbors and its neighbors' neighbors, and so on. And then you can build up a really large scale picture of what's going on throughout the entire hemisphere, and therefore rule out, false positives that are nowhere near what it thinks is really the lesion. So that's the theory. A little bit about how that, for those who are kind of interested in the nuts and bolts of the AI itself, we're using a graph convolutional neural network. It's a UNet architecture. And briefly what it does is you take in the input features. If this was a 2D image, that would be red, green, and blue. In our case, we've got cortical thickness, folding, flare, and these are the features that we put in. And then it goes through a range of kind of processing steps. There are some downsampling steps that extract coarser and coarser features, and so that a neuron in this neural network really at this bottom point can understand about quite a large portion of the brain what's going on. But you then also need to go back to this high resolution segmentation, so we have upsampling steps. And because it's not a nice regular 2D image, you have to have a slightly funny form of upsampling and downsampling on a mesh, which you can see here. So this is the very high resolution mesh, and you can do the downsampling successively, as shown with these different, they're called icospheres. And in terms of the task that we're training it to do, the main task we want it to do is to segment the lesions. But we also added a couple of extra tasks to help deal with what we identified was a mask uncertainty problem, which is that these lesions are very hard to mask, and they're not, manual lesion masks aren't always in exactly the right place. So one additional task is a distance regression task, where you say, if you're pricking out false positives that are very far from the lesion masks, that's worse than if you've got something that you think is lesion right next to the lesion mask. That might just be because they didn't quite capture it in their drawing. And this helps to reduce the number of false positives that are very far away from the lesion. We also have a kind of fail-safe, which is there a lesion anywhere on this hemisphere? Can you just recognize that there's a lesion somewhere here? And this helps to deal with the cases where the lesion mask might just be in the wrong place. It can still learn something useful that there should be a lesion somewhere on this hemisphere. But just to kind of recap, the main thing we're training this algorithm to do is to segment the lesions, and these just help the process. And so this is a kind of comparison for those that were familiar with the previous algorithm. That's the one on the left, the multi-layer perceptron. This is the brain paper that we shared, and I think many people may be using as well. You can see kind of what I was describing is that the red is the prediction and the black is the outline by the radiologist of where the mask is. And you can see that it's picking up the lesion in all of these cases. The red overlaps the lesion mask, but it also produces these false positives. So there's a false positive here, quite far away, which is just almost certainly wrong. Some false positives here, 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 and here. So it predicts the lesions, but there are false positives. And that means if you're looking for a new patient, you might have to review 4 or 5 areas that are suspected by the algorithm. By introducing context, the second column, you can see that it's now just producing one cluster. It overlaps even nicer with the lesion mask in almost all of the cases. And there's no false positives elsewhere on the cortex. And that's just 4 examples. But if you look across the whole cohort, where you might have previously had 6, 8, 10 clusters even predicted, we now very rarely have more than 1 or 2. And what this translates to is that the sensitivity is maybe slightly improved, mostly unchanged. The specificity is a little bit better, but the positive predictive value is much, much higher. So if there is a prediction, the likelihood that that prediction is in fact a lesion is now much, much higher than before. And kind of really importantly, the group that we want to make a big difference in, those that were MRI negative at some point, we're picking up around 2,000 of those lesions. And so this is a group that we really think these tools could help in. It says under review, it's nice to share that this is, has been accepted and should be coming out in the next month or so. This is one of the reasons we're now able to share the code with everyone. And so Mathilde, who's on the call here with us today, has she's done a lot of the coding here and done a fantastic job in creating this new subject prediction pipeline. And this is what everyone hopefully on the call is looking to download. What you give it is the input MRI scan. That's a T1, is absolutely essential. And if you have a 3D flare, so much the better. It can just do it on the T1 or with the flare as well. It runs all of the processing in the background. It will extract the surfaces, compute the features, carry out all the harmonization and normalization steps, run these features through the classifier, then wrap the predictions into a PDF report and a volume image that you can then go back and look at with the cluster highlighted in a particular color, in red and yellow. And I think in a moment, we're going to go through how to interpret those reports and what that looks like on your computer in terms of the files. Just as from our experience at Great Ormond Street, they now run this pipeline, and then they're able to take the PDF and the volume and upload them back to PACS, and then the radiologists can then review them with the other information. So are we able to copy that into the chat, Sophie? Or I can do that. I'll do it because I'm going to. So we now have a interactive notebook that takes us in a bit more detail. I'm going to put the link in the chat, and if you're interested in kind of running it alongside me, we can do that together. Here's one I have from earlier. And so if you click on the link that's in the chat, you should see something like this. It's an interactive tool that you can, it's just as a warning, it's not the full algorithm. It's just some example data and parts of the algorithm to demonstrate what it's doing. The full algorithm installation we'll talk about in a moment. So the first thing you have to do, and I would encourage you to start, you press Shift Enter, or you click on the little play sign here. This will install some of the packages you need to kind of run this alongside me. It takes about a minute to do so. And then we're going to look at an example patient from the Bonn cohort. So the group of Theodor Ruber in Bonn have made an openly available FCD cohort. So you're able to kind of look at this image. And this is one example patient. It's an 18-year-old male with focal epilepsy. Their seizures were not controlled with anti-seizure medication. And so they were investigated for a suspected focal lesion for epilepsy surgery. And as part of this investigation, they had an MRI scan. And we can now, if you kind of press the play button or Shift Enter, you can run this cell, so subject 00. It'll load in the MRI scan and the flare. And then we have a viewer here. And what we can see is an interactive viewer with a slice. You can only look in the coronal section. So if you're coding along, you can slide that dial and it will regenerate your image. I will take us through a few slices to try and see if we can spot the MRI, the lesion, just by looking through the MRI scan. So I'll do a slice, wait a few seconds, and then I'll go to another point. Wait a few seconds, and then I'll go to another point. We're not really expecting you to get it, but just to get an impression of what this brain looks like. And I know where the lesion is, so I've made sure we stopped at a slice that showed it. If you're running it yourself, you can have a little bit longer to have a look at those different slices, but we'll go once more through just to give people time. I think if you're a radiologist, you might be used to a nicer viewer, but at least this works for us all online. Okay. So we've gone through it, and I guess we'll go now to our Menti question of how confident are you that you know where the lesion is? So I will just click us through to the next slide on this. And so here we go. Question 1 on the work on this interactive tool, we're trying to estimate lesion confidence, where the far left is absolutely no idea. The far right is I'm pretty confident I know where the lesion is. And in between that is, there's a couple of areas or a few hypotheses. we'll aim for around 30 responses before we, so once you've give people a chance to load up the Menti again, that's the code is 88010577. Give people another minute to have a go. And so we've got a good range of confidences, understandably, given how quickly we went through that and how these FCDs are hard to find. There's a group that have very little idea, a couple of people who everything looks a little bit abnormal to them. There's a few people who have a suspicion, but not super confident. And there's a few people who are a little bit more, I think I might know where it is, but would want a little bit longer to be certain about that. Okay, lovely. I will now move us on to having a look at, so we've got an average of 2.2 for now. That's great. So we're now going to have a look at 3 of the surface features: thickness, W minus G dot PCT is white minus gray contrast, so that's T1 contrast, and we'll look at the flare intensity. So we'll run these next couple of cells just to plot these onto the surface and see what they look like in their initial form before we do any kind of normalization on them. And while that's
this
running,
comes from FreeSurfer, right?
yes. So in the background, we've already run this through FreeSurfer and extracted the features and mapped it to a template frame. Yeah, it's a great point. And so what we can see now is cortical thickness. In red is where it's thicker, and in blue is where it's thinner. And you can see that there are variability in this feature across the brain anyway. We can see, a patch that looks thinner here, maybe at the back. We have gray minus white contrast. So this is the T1 contrast between the gray and white matter. Again, red is high, blue is lower. And we have flare intensity sampled within the gray matter. So just quickly looking through those again, got thickness, contrast, gray white matter contrast, and gray matter flare intensity. And we have a second question now about, having seen these features mapped to the surface, how confident now are you about the lesion location? So we've seen those 3 features. Same question, has that changed your impression at all?
Just a quick question. Your initial MRI was shown in radiological orientation, right?
Yes. So yes. So left is right, right is left, and this surface is right
hemisphere. Yeah. Exactly. Thank you.
So that's actually a clue.
A clue. Yeah.
Definitely, yeah. Well observed. I'll give you that. It's on the right hemisphere.
Oh, I know.
Okay, just seeing how many counts we've got. We've got about 20.
Just give it a little bit longer in case anyone else wants to join in.
Yeah.
And just a reminder, you can go to menti.com on your phone and use code 88010577 to see these questions.
Join in, yeah. Okay, so it looks like we've had a small increase in our confidence. I think we were about 2.2 before, and as a group, we're now at 2.9. So getting further towards the right, which is, I think, the right direction. So I'll now take us on to the next part of this processing, is that we 2 challenges in identifying abnormal features are that you have inter-subject differences and inter-regional differences. So to deal with inter-subject, we Z-score within subjects. That means removing the mean standard deviation that's specific to the subject. So children will have thicker cortex than older adults, and you need to adjust for this. The second is this interregional pattern, which is that in different parts of the brain, there's very characterized patterns of these features. So if we look at thickness averaged across our entire control cohort, we have a very thin central sulcus. We have a much thicker frontal cortex. We have a thin occipital cortex. And therefore, we need to adjust for this pattern to find out what's abnormal also for that brain area. And so we use this average map to kind of regress this impact out of each subject's map to really highlight what's abnormal. And so we can now look at those same 3 features again, this time having done the inter-subject, the asymmetry calculation, and the intra-subject normalization. This is the kind of end point of that pre-processing. These are the features that really go into the classifier and help it to make it just, this is what it's trying to learn, looks like an FCD or not.
And just a reminder that if you want to run this notebook, you can just click on the link that's in the chat and you just press the play buttons by each cell. You do need to do it in order. So you need to start from the top of the notebook and go down.
The bottom. But also if you would, you're very also welcome to just watch along and join in through the Mentimeter because so as not to get lost. So now we're seeing a much different pattern. There's no big, large scale patterns. It's quite smaller variance. Higher frequency variability. And what we're looking for is clumps of vertices that are abnormal together that might be a lesion. And so this is cortical thickness, abnormally high or kind of slightly higher thickness is red and lower is blue. Contrast, again, high contrast would be red and lower contrast areas would be blue. And then flare, so low intensity flare is blue and high intensity flare is red. So we'll just quickly scan through those again. Thickness, gray white matter contrast, and flare. So having seen these pre-processed features, let's do the third. We've got 4 in total. The third time, how has this changed anyone's opinion of where the lesion is or made you more confident about where it might be? Yeah, we've got about 20. I'll give another minute. And I think one of the reasons we're going through this step by step is to kind of help give intuitions about how the algorithm is defining where these lesions are. And that might then help you interpret its outputs later on when we go through the report.
But again, those features that you have extracted for the phone normalization, they also were extracted using free surfer pipeline.
Yes, it's all the same free surfer.
Yes.
Okay. So just see if there's anyone. Great. I can see that the confidence has again gone up another point. We're now at 3.7, with most people either having a rough idea or starting to feel quite confident about where they think the lesion is. And so the last part of that pipeline is that you would then feed these features into the classifier. I've kind of gone over this architecture before. It sees these input features. I've shown you 3 of them, but it actually ends up with 32 different features that it sees. And it will look at patterns across these features and also patterns across the surface to try and find where this lesion is. And it's seen a couple of hundred examples of these lesions in the train cohort to learn these features. And it's then evaluated on a new example, like the one we're going through now, to see if it can figure out where the lesion is. And so we can run our new patient, their features through this MELD Graph algorithm, and we can look at where the prediction puts it. So it's, I don't know if this is where people were thinking, but it's right hemisphere, occipital cortex is where. Pardon?
We're going to ask them how.
Yes, this is where the prediction is. And so this prediction is then wrapped into a prediction report. Let's just, yeah. So in this report, it gives you the location of the lesion. The red is a large area, and the yellow is the points on that surface which are really driving this most strongly. It's the most salient vertices. So they're the areas that are kind of most abnormal. We can also map this back to the volume, so you can go back and look at the volume. And then you also receive for every predicted cluster a report of the features that the classifier quantified, and which is sort of the X deviation, but the color is how important it was to the classifier in making this decision. So this lesion, the classifier thinks it's an FCD because it has a reduced gray white matter contrast, increased cortical thickness, and reduced gray matter flare. And then you can go back to the original MRI scan and look at that point on the surface that it's thought was a lesion and say, yes, these features look like an FCD to me. I understand that. Or no, maybe it's a false positive or a problem with the pipeline. I think this is not an FCD, and you can rule out false positives that way. And so now, last time, how confident are you now about the lesion location with the report in hand? Do you think that the classifier is right, having had a look at it, or do you think it's still not sure? I would want to have, SCG or PET to confirm that. We've been consistently getting to about 20, so thanks for people to. Okay, we've hit 20 and everyone is pretty confident. They think the lesion's there, that the classifier is correct. We'll toggle once more to find out what the answer was. So we can have a look at where the radiologist, after the surgery, drew on the lesion mask. Well, I think the surgery confirmed that it was an FCD. So after surgery, this was confirmed to be an FCD. And I think we've got the images the wrong way around, but this is, it's a right hemisphere lesion in the occipital cortex, exactly where we are now all quite confident the lesion is. And this is in fact the correct location. And I hope that kind of, we can just quickly go through the answers. We went from relatively low confidence, just looking at the MRI. We used the features to kind of start to put some hypotheses together. That increased our confidence. And then by the end, we were all pretty confident with the lesion report that that was in fact where the FCD was. And so for those who've been coding alongside, we're not going to go through it together now, but there's another example. So patient 0 was considered a visible lesion that lots of people could be able to see it. Patient 1 is an example of someone who was MRI negative after being viewed by many, many reviewers. So it's a much more subtle FCD, and it's the kind of example that you could really make a difference in. So if you are interested in running it through in your own time, you just go up to the top and replace sub 00 with sub 1, and then you can carry on running through and it will load everything for you.
It doesn't have the report at the end, so
okay, no report. Yeah, but it does the prediction. Okay, great. So we are, I think I'm now going to pass back to Sophie. So we've done overview of the algorithm and a notebook that kind of takes you through the logic of the algorithm. And now Sophie's going to take us through the reports.
Thank you. So you've run your algorithm on your patient, which we're going to cover exactly how to do that later. But just now you want to look at the outputs and understand them. And the first thing you need to do is you need to quality check them. So I'm going to be showing you a video now of what the reports look like, how to look at them, and how to quality check them, which me and Mathilde put together. And then we're going to show some examples of outputs in some MRI negative patients. And then we're going to talk about how we've begun to think about translation into clinical practice. So I'm going to click on the video now. If there's any problem hearing it, let me know.
This video covers how to interpret the results of the MELD Graph pipeline. You will find the guidelines on our GitHub at MELD project MELD Graph, and you will find the full documentation by clicking here. So we can go directly to the interpretation of the MELD Graph pipeline results. The MELD Graph pipeline output a PDF report, which summarize the results of the pipeline and also the prediction as a Nifty file. And in this tutorial, we're going to show you how to interpret the PDF report and how to quality check your prediction as a Nifty file.
What you want to do once you've run the MELD Graph MELD Graph algorithm is to interpret your results. So in your MELD Graph data folder, there's a folder called output, and in the output folder, there's a file called prediction reports. In here, for each of your subjects, there will be a folder, and if you open that folder, there will be some folders called predictions and reports. And in reports, there's a PDF file called MELD report and your subject ID. And I'm going to show you an example of one now, and we're going to interpret it together. MELD report, the first thing you can see is that it's for patient subject 00003. And the next thing that you can see is it tells you some information about what algorithm has been run. So this patient has been run through the MELD Graph surface-based FCD detection algorithm. On page 1, you'll see an overview of all the detected clusters, and then each subsequent page will be detailed information about one cluster. Just the disclaimer that this is MELD Graph surface-based FCD detection algorithm is intended for research purposes only and has not been reviewed or approved by the Medicines and Healthcare Products Regulatory Agency, MHRA, European Medicine Agency, or any other agency, and any clinical application of the software is at the sole risk of the party engaged in such application. There is no warranty of any kind that the software will produce useful results in any way. Use of the software is at the recipient's own risk. So there's the disclaimer. So then what you see is where clusters have been identified. So in this patient, one cluster has been identified in the right hemisphere, and this is where it is. We go to the second page. You'll see the cluster on the T1 in red, and in orange, you can see the most salient vertices. So those would be the voxels that were used to drive the classifier's decision. And below, you see the T1 without the cluster, so you can see the same area and see whether it seems to have any abnormalities. Next, you have some information about the cluster. So this is a cluster on the right hemisphere. It's around 8 centimeters. It's in the supramarginal region. And the classifier is around 80% confident that this is an FCD, so it's fairly confident. It also tells you the voxel value on the NIFTY, which is 1 in 100. So if you were to go back to the NIFTY prediction, any voxels that were labeled 1 or 100 would be part of this predicted cluster. And then you can see each of the features, and you can then see how abnormal they were, which is the Z-score, and how salient the color is, how important was that to the classifier. So for this example cluster, one of the main features that's been used to drive the classifier's prediction is the cortical thickness. This has a Z-score of around 4 for the normalized cortical thickness. And you can see that it's a kind of dark pinky color, so that was important to the classifier. It's also characterized by blurring of the grey-white matter boundary with a Z-score of around minus 1.8 and some flare hypointensity in the grey matter with a Z-score of about minus 1.5. So those were the main features used to drive the classifier's prediction. And this is important because you can now go back to the cluster. You can open it on your T1 and view it with your flare data and see whether the identified area has any of the features that we described. Does it have increased cortical thickness, blurring of the grey-white matter boundary, and on the flare, do you see hypointensity?
It is important to quality check the results of the pipeline to check and ensure that the predictions are not due to obvious free surfer reconstruction errors or scan artifacts. For that, you can use the scripts that we created and that will automatically load your results on FreeView, which is a viewer of FreeSurfer. We are now going to do this together. Here I have my MELD Graph folder, which contains the MELD Graph pipeline scripts and my MELD data folder. So I'm going to go into the MELD Graph folder and open a terminal there. If you have the Docker version of the MELD Graph pipeline, you can follow these instructions here. It is important to note that Docker does not allow GUI interface. Therefore, you will need to have a standalone installation of FreeSurfer or FreeView to be able to use QC scripts. However, if you have a native installation, you can follow the guidelines that are provided here. So for the Docker installation, we are going to first export our FreeSurfer home. So once you have installed FreeSurfer as a standalone, you can export it. So I'm going to replace this path by my FreeSurfer installation. And then I can source it to activate the environment. So you can see now that FreeSurfer is activated in data folder, which is this one. And we can enter. And you can see that it is opening FreeView and it is loading your T1 scan, your flare scan, the prediction on the left and the right hemisphere, and also the left and right surfaces. So what you can do from here is, for example, remove the flare so that you can see the T1. You can also, by clicking right and moving your mouse, you can change the size and make it bigger or smaller. You can also move on the brain by clicking left on your mouse and moving. And what we want to do is we want to find the cluster. So I'm going to look for my cluster. And I can see it here in blue. You can remove the surfaces if it's easier to see. So I see it there. And I'm going to put the surface back to check that the surfaces might not have been a problem here. So you can quality check that the surfaces seems okay. And you can also layer back. You can go back on the documentation and you will have more information about how to QC and what to check for the surfaces and the cluster.
Okay.
Okay, so that was how to quality check. Just as an example now, so Conrad covered before this patient one, that was the example that he gave. And now I'm just going to show you some output reports in 3 patients who were missed by 5 expert raters. This is patient 2. You again can see where the classifier predicted. It's only 7% confident. So this is one where it's a very subtle lesion, but it thinks there may be an abnormality in this location. And the reason is mainly driven by abnormalities in the flare. Again, the next example, it's a little bit more confident, 45% confident, and this time driven by blurring of the grey-white matter boundary, reduced flare, and some abnormal folding. And the last example is one where, again, the cortical thickness is really helping to find this lesion. So now we've got these reports, how can we think about potentially using them? And we've been doing this in a few different ways, working with the radiologists, working with the surgeons, and also hopefully through training lots of people worldwide in how to use these types of technologies. So just in terms of translating into clinical practice with the radiologist, going back to our 8-year-old girl, we've run our algorithm, we've identified this area, and this report can then be reviewed, and the MRI can be re-reviewed by the radiologist to see if they agree that this area is a focal cortical dysplasia. We've also used the MELD algorithm to help plan SEEG implantations. So in this study, patients who were being implanted for stereo EEG who were MRI negative, we ran our algorithm on them, and if any areas were identified that were not already going to be implanted, we could add extra electrodes in, provided there was no clinical or safety concern not to. And lastly, at the National Hospital for Neurology and Neurosurgery, they've been using the PDF reports that the algorithm outputs and using them as part of the discussion in the epilepsy surgery team meetings. So just back to menti.com, and we'd just be interested to know how you're planning to potentially use the MELD Graph algorithm. So it may be that you're planning to feed it back to the radiologists to help it for neurosurgical planning, to be discussed in the surgery meeting, purely for research purposes or as well for research purposes, other or not really sure. We'll just give people a little bit longer because it's really helpful for us to know how people are trying to use it. And I know that we've got about 60 people on the call, and so far about 30 have responded. So if you haven't, do just go to menti.com and use code 8801577, and you should just be able to click on how you're planning to use MELD Graph. Okay. Just give it a little bit longer. By the way, I just wanted to mention, if anyone has any questions, now's actually we're about to have a time for some discussion and questions.
But throughout, if there's anything that comes up through this or the next section, please also feel free to put them in the chat, and we'll either Matilda will be able to respond, or we can deal with them as well. Okay, I think that's probably
okay.
So we got a nice distribution there of radiology, neurosurgery, and epilepsy surgery meeting, as well as for research studies. I would say that if I was reflecting, I think we found that working with the radiologists requesting this, if you can get them on board, is in some ways a quite good way of dealing with it, because they're quite used to dealing with kind of different sequences, and this would be, in their mind, an additional kind of test that they integrate together. All of these in theory work, but our experience has been the smoothest has been with the radiologist. Would you agree with that?
Yeah, I'd agree with that. I think that the radiologist then being able to then on their PAC system load everything up and relook at these areas has been the easiest way to kind of confirm or rule out these identified areas. Okay. So we are at the end now of the point about the talk on the MELD graph, the interactive notebook showing you kind of under the hood of what this algorithm uses, and then kind of how to look at the outputs. What we're going to be doing next is a much more kind of step-by-step what you type into your terminal window, how do you prepare the data, how do you compute the harmonization parameters, how do you run the prediction pipeline. So we're going to pause at this point for discussion and questions. And at this point, I just wanted to highlight a few things. Firstly, that we will be running another workshop in January on the 30th, again, same time as today. And this will be to teach you how to use the automated detection of hippocampal sclerosis algorithm that we have called AID-HS. This has just been published in Annals of Neurology, and we're really excited to share that with you. So just a date to put in your diary. And secondly, we would really, really like feedback on the workshop. So we're going to put the feedback link into the chat now. And while we are doing the discussion and questions, if you could provide feedback for us on the workshop and on kind of how you're planning to use MELD, that would be really fantastic. And then the last thing before we go into discussion is just to let you know that we are collecting data for the MELD focal epilepsy study still. A lot of people on this call have already contributed. We've got 30 centers who've contributed MRI data for that. This is across multiple different pathologies. So we have FCDs, but we also have hippocampal sclerosis, long-term epilepsy-associated tumors, cavernomas, polymicrogyria, hypothalamic hamartomas. So if you have patients with those pathologies that you think you could contribute, do get in contact. And now we will go to questions before we go to kind of the step-by-step how to do this. So do you feel there's a lot of people on the call, so I'm going to go start with the chat, but
also, for those that need to leave now and you've had the kind of in person, we have recorded, Matilda's done a fantastic job of recording videos of all the stages as well. And those you can be linked through GitHub, and that will also take you through step-by-step this process. So that resource is there as well. So have a look for questions. And also, if anyone wants to unmute and ask them, we can also take them live. Should I stop sharing my screen for a moment?
Yeah, let's stop sharing the screen and we can monitor the chat. And also we hopefully will be able to see if people have raised their hands. So the first question in the chat was how to incorporate the MELD findings onto the 3D-T1 and review it on our PACs. And Matilda has a lovely script that does that so that you can see them fused together and load it in an MRI viewer. Okay. Are there any other questions?
One about how to export the probability mask in surgical planning. So that's, I guess it's a similar question. So as part of the output pipeline, you get this nifty format. So it's not in the DICOM format. So nifty.gz format, where you have what is underneath the T1, and just where it thinks the lesion is this colored object. Depends on the software that you use then for your surgical planning. If you use Slicer or many of these softwares would expect nifty format, and that you should be able to just load it in, and that should be in the same space as your original T1. In terms of actually uploading it back into PACS, I think you would have to convert it back into DICOM and then upload it, but yeah.
We've had another question from Ahmed, who's asking, is it possible to use other modalities such as Edge, MP2 Rage, or DIR, WAMN images? So at the moment, we did a survey before we trained this algorithm on what modalities most people had and could share with us. Oh, white matter MELD, sorry, I was... and basically the modalities that most people had were in 3D format, were T1 and FLAIR. So that's what we've trained the algorithm on. So currently you can't evaluate it on, you can't run any additional sequences into the classifier, but obviously you can evaluate it alongside those other sequences. And alternatively, we do have all the code. Yeah, so we always make a big effort to make our code as open as possible. All the code for training these algorithms is available through the GitHub. I mean, it's a bit involved to get in there, and we are thinking about ways of how people could train their own versions with their own set of sequences. It's something we're interested in building. But at the moment, it would be a case of looking through the code, figuring out how it uses T1 and FLAIR, and adding your edge sequence into that too. And then you'd have to sort of train your own local algorithm. The cost is you'd lose this huge data set that we have. You'd lose access to that as part of the training. You end up with however many patients you've got edge on. And that's why we've made this decision to prioritize the most common sequences. Tatiana, you've got your hand raised.
Yes, thank you very much for the floor. If I know anything about FreeSurfer, is that as the first step in any pre-processing and surface creation, it downsamples any MRIs to 512 by 512 grid. So kind of it's really heavy downsampling compared to the resolution that we get in the clinical MRIs. Therefore, is your algorithm based on this downsampled data, or are you trying to do high resolution surfaces first?
So we use the FreeSurfer downsampling. That's to 1 millimeter isotropic. So for most people, that's not heavy downsampling. I mean, I know some sites acquire higher resolution data, and in that case, there is a bit of a loss of resolution. But for most clinical sequences, certainly in what we've received, that tends to be not a big downsampling step.
So do you expect the algorithm will perform better if you use high resolution surfaces?
I would say that at the moment, it probably wouldn't, because if it's just downsampling it to 512, it'll look like, I mean, unless there's some improvement in the signal to noise ratio and it looks nicer even at 1 millimeter, there wouldn't be a big bonus. And I'd say that FreeSurfer is really optimized for that resolution. And actually, if you start to push it to higher resolutions, it starts to not really know what to do with it so well. So, I mean, if someone is using 0.5 or 0.7 and we don't have that data, so we don't really know, we'd be very interested to hear how it's performing on that data.
We have another question from Mark that's asking that they've got some inhomogeneities in their sequence, but it's always the same across their patients. Would you recommend including it in the pipeline or just using the 3D T1? It's a really good question. I think I would probably suggest it's once you've got the algorithm installed, it's quite simple to run it with and without the FLAIR. And so especially taking initially some patients where you know where the lesions are, I would suggest running it both ways and seeing how it performs.
And just to add to that, this is, oh, go ahead, Mathilde. Yes, go.
Sorry. So what I wanted to say is that I think we would also recommend to do harmonization, because that's what harmonization is for, is to actually remove any scanner bias, and that's clearly a bias that you have on your on this specific sequence. So if you have few patients that have been acquired with this specific sequence, you can, if you have 20 patients specifically, or 20 subjects even, healthy controls, you can run the harmonization step and then just run the algorithm with this specific harmonization parameters to remove the bias.
Exactly. So harmonization is trying to learn from your specific scanner what everyone's scanner has that kind of effect to a lesser or greater extent, and harmonization is really trying to learn that and make your data look like our training data so that we can treat it like a flare that we've seen before. But as Sophie said, I would also test it with and without, because we have found that some really different flare sequences make things a bit worse. So it's worth checking that that's not happening. And it works pretty well with just the T1 as well.
So the next question by Ahmed, which is a really good question, is do you need to co-register your flare to your T1, or does the pipeline handle it? The pipeline handles it, so you don't need to co-register your data first. You just need to place your flare into the flare folder and your T1 into the T1 folder, which will be covered in the how to run the algorithm part, and the pipeline will do the co-registrations for you. And the next question is, does harmonization need to be run on the new algorithm again, or can we use the previously performed combat?
Mathilde, you looking?
Yes, that's a very good question. So you can use the same patients to run the harmonization. So for example, if you already have extracted your patients with FreeSurfer for the previous MELD classifier, you can use those patients. So you don't need to redo the FreeSurfer segmentation. However, you will need to redo the combat harmonization because we have changed slightly the preprocessing. So we have changed the smoothing of the data, for example. So you will need to recreate the harmonization parameter for this new set of features that have been slightly changed.
And I think that's worth also noting that generally, again, if you kind of upgrade your sequences so that the images look significantly different, that would be another case for harmonizing again. Okay, I think we will, so one or two of us will definitely stay online for the next few minutes, but otherwise I think we'll take what Americans call a bio break, a few minutes if anyone needs to run to the toilet. We will start the next section, which isn't going to take the full hour, at 10 past. 10 past?
Yeah, 10 past
10 past
2.
2.
10 past 3 in Europe.
10 past 3 European time. Yeah. Yeah, so we'll be back. But if anyone wants to hang around, I'll be here till then.
And do not forget to